All right, so this class we're going to talk about something called collision theory. Collision theory explains why certain rates of reactions are affected by certain factors. So it explains the entire mechanism behind rate of reactions. Within collision theory, we'll talk about effective collision and activation energy. And then finally, two different diagrams, a potential energy diagram and a kinetic energy diagram, which is also called the Maxwell-Boltzmann diagram. So let us first start with collision theory. All right, so collision theory is established upon several claims. The first one says system consists of particles that are in constant motion. And the speed of those particles is proportional to the temperature of the sample. So basically everything is moving around randomly. And the higher the temperature, the faster you move. Okay, so that is claim number one. We know this to be true. We learned this already. Kinetic energy is just average temperature. Second, in order for a chemical reaction to occur, there must be collisions between those particles. So particles, if they want to react, they can't just swim around. They got to hit each other. Only if you collide could there be a chemical reaction. And within collisions, there's effective collisions and ineffective collisions. Excuse me. An effective collision must have two things. One, it must collide with sufficient energy. All right, you can't just simply walk up to each other and bump. Okay, that is not enough energy. If you don't collide with sufficient kinetic energy, nothing happens. You just bounce apart again, and you don't react. If you collide with enough energy, also the second thing you need is correct orientation for the bonds to be broken and the new bonds form. So you can't just hit at any angle. You must hit at a specific angle and a specific orientation. Only then can you have a reaction. So that will be an effective collision. An ineffective collision will result if you don't satisfy one of the two conditions. You either didn't hit with enough force or you didn't hit at the right angles. Okay, so the particles will simply just rebound and nothing happens. All right, so 3. The rate of reaction, therefore, would depend on the frequency of collisions, and in those collisions, also the fraction of the collisions that are effective. So the more effective collisions you have, the faster your rate of reaction. All right, so here's a picture to illustrate what I mean. So collision theory says chemical reactions occur only if reactants collide with proper orientation and enough kinetic energy. So in the first two rows in the picture, you have NO plus O3. All right, NO smashes in with O3 in the first row. The oxygen is hitting the ozone. The product, well, nothing changed. They just bounce back, and that's exactly the same as reactant, so that is ineffective. In the second row, NO still collides with O3, but this time it is the nitrogen that collides with the O3. And yet again, the products simply bounce back, and that is the same as the reactant, so nothing happened, ineffective. But in the last row, NO collides with O3 in a different angle, in that specific angle right there. Only then will you get a chemical reaction. So it becomes NO2 and O2. So that will be an effective collision with enough energy and with the proper orientation. All right, so consider this. Okay, octane is gasoline. We use gasoline in automobiles and we burn them for energy. And it's very flammable for that reason. Octane reacts with oxygen with this reaction, and this is a really violent exothermic release of energy. It is so violent, in fact, it releases around 10,000 kilojoules with just 2 moles of octane. And if you don't really control that, we call that an explosion. Well, gas stations are full of octane. And the atmosphere on Earth is rich in oxygen. So here's my question. So why don't gas stations explode? Right? You have both reactants present. Oxygen is everywhere, octane in the gas station. So why don't gas stations explode all the time? Anyone want to answer that question? No? Think about what you're not allowed to do at a gas station.
Smoke.
Smoke, but why?
Because it's have heat, which will like a catalyst for the reaction to happen.
Exactly. Okay. You cannot smoke. Well, not just smoke. You can't have a flame at all, right, at a gas station because you might cause an explosion. So gas stations don't explode by themselves. They need something else to get them started. You see, and that will be activation energy. Okay, so to think about why gas stations don't explode, we have to use collision theory. So recall, you need two things for effective collision. One is proper orientation. The molecules must collide at the perfect angle in order for this to work. But that's not enough. You also need sufficient kinetic energy. If you don't hit hard enough, still nothing happens. So under normal conditions at a gas station, it is not too warm. So the molecules, the oxygen and the octane, while they're in contact with each other, there's not enough energy for sufficient kinetic energy in order to cause a reaction. So you can't have an effective collision. So this is called the activation energy. Activation energy, the symbol is E subscript A. This is the minimum amount of energy that you must have in order for a reaction to be successful. If you don't have this activation energy, even if you have all of the reactants, nothing's going to happen. All right, so why do we need activation energy? Well, because in order for molecules to collide, they need force. Okay, because the nuclei of different atoms, they actually repel each other. So if you actually get too close, the nuclei gets too close, it repels. So in order for them to smash in, you have to actually use a lot of energy to overcome that repulsive force. So that's why you need high kinetic energy, otherwise it's not going to work. It's like imagine bringing two magnets together. If they have the same pole facing each other, it's going to get harder to push them in as you get closer, right? So you need to input more force. So gas stations don't explode because they lack this energy. The molecules do not possess sufficient kinetic energy in order for this to happen, so it's quite safe. Unless, of course, you do something really stupid, you go to a gas station, you whip out a cigarette and you start smoking. Then what you're essentially doing is you are providing this activation energy for the reactants, right? Because they didn't have enough energy to collide sufficiently. Well, okay, let me light up a flame and heat it up for you. So if you do that, then some molecules at the gas station will heat up and they will collide with enough energy now, which will cause a combustion reaction which releases more energy, and soon it is an explosion. So this is why you cannot smoke or just light a flame for any reason near a gas station because of chemistry, activation energy, okay? So if you want to describe activation energy with a graph, well, it would be akin to something on the right. That is a potential energy diagram. Imagine that you have a ball trying to roll down a hill. Naturally, you would just roll down the hill, but you have a little, hill on top you have to reach before you can roll down. So you have to get over that hump. And you need energy to get over that hump. But once you're at the top, it's very easy for the ball to just roll all the way to the bottom to reach B. But in order to reach B, you must have at least that amount of energy to get it over the hump in the first place. And that would be activation energy. All right, it's like a potential energy barrier. If you don't give the ball any energy, it will never reach B, despite the fact that B actually has lower energy than A, so that is more desirable, but you're not going to get there. So you need sufficient kinetic energy in order for a reaction to happen, even if it's exothermic. So what happens, in fact, is when the two particles are far apart and they're headed for each other, they have high kinetic energy because they're moving, but as they approach each other, they slow down because of the repulsive force. And because the nuclei will start to repel, they slow down as they get closer, so kinetic energy is being lost. It's getting slower. But potential energy is increasing because you're getting closer. The closer you get, the more tension there is between the two particles. The closer the two nuclei, the stronger the repulsive force. So that is potential energy. So kinetic energy is converted into potential energy as they come close. Once they collide, you're at the top of the hill. And when they finally break apart again, the potential energy decreases as they go farther away from each other, and also they become faster now, and it's converted back into kinetic energy. All right, does that make sense? And you can use the hill analogy to understand this. You have certain energy in the beginning. You need a little bit of input of energy to get over the activation hump. And once you're there, you're free to then react and become a lower energy state, which is B. Okay, does that make sense, guys? So that's what the activation energy is about. You need to overcome the electrostatic repulsion of the molecules. All right, so here are two more potential energy diagrams. Now this time you can see the difference between an exothermic reaction and an endothermic reaction. With an exothermic reaction, the final product will have lower energy than the reactant, so energy is released overall. But you still need an activation energy to get this started. But for endothermic, your product have higher energy than the reactants, so energy is absorbed. But again, you need activation energy, and this is even higher than the energy of the reactants. In both cases, you have to get to the highest point, and at that point we call the activated complex. What is the activated complex? Well, for a split second, the two colliding molecules will be linked together. All right, everything is connected as one big molecule for just that split moment. The next moment, it will just start to break apart again. So imagine it's like somebody took a photograph. Someone kicked a soccer ball, hit someone in the face, and this photographer just happened to take a photo the moment the ball hit the face. And there are actually photos like that on the internet. You can see that the ball actually crunches into the face. All right, but we know that that is a highly unstable state. The ball would just fly right off at the next moment. But at that moment exists the activation complex. Okay, that's why it has the highest overall energy, because it's so unstable, it is ready to break apart, and it does break apart. It breaks apart into the different products. Okay, does that make sense? This is also called the transition state. Now here in this diagram, it's the same diagram, except it illustrates what happens to the molecule at every step. So you have BrCH3 plus OH minus. So in the picture to the far left, you have two molecules flying into each other. They're about to collide, but they're still two separate molecules. As they get close, you can see that the central carbon is slowly forming a bond with the red oxygen, but that carbon also has a bond with bromine. So right now it kind of looks like it has 5 bonds, which is not allowed for a carbon. So instead, look at those dashed lines. That represents like half a bond, like a partial bond. This bond is slowly starting to form, and that bond is slowly starting to break. And in the middle, when you have the highest energy, that is the activated complex, with carbon with almost 5 bonds, 1 bond with oxygen formed like halfway, another bond with bromine broken halfway. So right now, temporarily, you have 5 bonds. And then slowly, the bond with the oxygen becomes stronger and stronger, and the bond with the bromine becomes weaker and weaker. Eventually, when they fly apart, The bromine is separated from the molecule. The carbon makes a new bond with oxygen. So that is a way lower state of energy than the activated complex. So this is an exothermic reaction. Okay, so that's what happens to the shapes of the molecules as the reaction progresses. If you look at the diagram, on the x-axis you have reaction progress. That means time. The y-axis you have the amount of energy. With a potential energy diagram, you can label certain things from the reactants to the very top, the activated complex. That difference is EA. That is the activation energy. That is the amount of energy you need to get your reactant to the activated complex, and then you can have the rest of the reaction. The difference between the reactant and the product is the enthalpy. Okay, the change in enthalpy, delta H. We talked about this already. And you can look at this reaction backwards, in reverse. You can imagine that the product combined to become the reactant. And in that case, then the activation energy would be from the tip, the activated complex, to all the way to the bottom, the product. And so if you want to imagine this going to the left, you can. So that will be the new activation energy to go backwards, which is really high. And so does that make sense? If I give you a diagram and ask you to label something like that, you will be able to do that. All right, so here is something quite confusing. I believe there's a student here. So this is something called a Maxwell-Boltzmann distribution. You can graph energy as well as a number of molecules using this graph. The graph I showed you earlier is called a potential energy graph. This one uses kinetic energy instead. So this one is a little bit hard to understand. So imagine this thing. Okay, you have the x-axis, kinetic energy. That's how fast you're moving. You go from 0 to a really high number. On the y-axis, you have the number of entities. So how many molecules exist with that kinetic energy. And you can see that most molecules have an intermediate kinetic energy in the middle. Very few has really high kinetic energy, and very few has really low kinetic energy. Exactly 0 molecules have 0 kinetic energy. You can't have literally no kinetic energy. That's not possible. So this actually originates from the origin 0, 0. It's like a normal distribution. Imagine that this is the grade distribution for this class. Some students are getting 90s, okay, by very little. Some students are getting really bad marks, like failing. Most students should be in the middle. Okay, that's usually what happens in a classroom. Most students get 70s. There are some higher marks, 80s. Very rarely do you see a 90, and then some students are 60. Very rarely do you see somebody failing. Okay, so high in the middle, low at the end. If you see that vertical dashed line that's labeled activation energy, well, that line is the cutoff. That is the amount of kinetic energy that will enable reaction to happen. So only if you are a particle that has higher energy than that, if you're found on the right side of that dashed line, you will be able to react. Okay. Anything found on the left side, that means you're too slow. You don't have enough energy in order for this to happen. And the area under the curve represents the total number of particles. Okay, did that make sense? So this is telling you that the area shaded in blue, the area under that part of the curve, are the total number of particles that have enough energy for a reaction to occur, and it's not a high percentage. So hence, you have a relatively slow rate of reaction. Okay, do you understand how to read a Maxwell-Boltzmann distribution? You compare the kinetic energy to the total number of particles. So any questions? Okay. Now let's use collision theory to explain the 5 factors of reaction rate. So how does temperature affect reaction rate and why? So recall that increasing temperature, you get a faster rate, right? Well, this is because if you increase temperature, you are increasing average kinetic energy. They're the same thing. So if you increase the kinetic energy, the molecules will move faster. So you have a higher percentage of molecules that would have enough activation energy, so you have more collisions. So this results in a faster rate. To represent this on the graph, you can see that there are two curves. So x-axis is still kinetic energy, y-axis is the number of molecules. So if you look at the blue curve, this is the distribution before you heat it up. All right, so like you saw earlier, most of the molecules have intermediate kinetic energy, very few has low, very few has high. And if you draw the line down to the right, you have a vertical line, that is the activation energy. Shaded in green, very little, pathetic amount of molecules can have enough energy to react, so you're really slow. If you manage to heat this up, you get the green curve. It's like you took the curve and you pulled it to the right. So now, once you heat it up, you increase the kinetic energy. So now more particles will have sufficient energy in order to react. So now you have a higher fraction of effective collision. So therefore, higher reaction rate. All right. Keep in mind that the areas under both curves should be the same. Right? They have different shapes, but their area under the curve should be the same because you didn't change the number of molecules. By heating up a substance, you're not gaining molecules, you're not losing molecules, they're just moving faster. Okay, if you find that difficult to understand, just imagine like a classroom, let's say this class, okay? Let's say that, for your midterm report card, I put in your marks, we're like, oh crap, the average is 55. Yeah, that's not gonna look good. The students are not going to be pissed. Your parents are going to be pissed. The school is going to be pissed. Are you doing something wrong? So I look at my test. Did I make the test too hard? Oh yeah, I accidentally put like second year university stuff on here. Whoops. So you know what? I have to save you. I have to save your marks. The average can't be 55. That's a little low. So you know what? On the next test, I'm going to make it kindergarten level. Okay. If you have a brain and can see, you should be able to get perfect. So I'll give you that test, and voila, the marks go up. So the average now increases. Whereas before at the midterm, when I can give you a hard test, 2 students got over 80, let's say. Well, that sucked. After I give you the third test, 10 students now have a mark over 80. I was like, oh, okay, that looks much better. I probably won't get in trouble for that. I won't be inspected and I won't be questioned. So basically, that's increasing temperature. By making the test easier, more students are able to do well. So the average goes up. A greater percent of students now have a mark over 80. Does that make sense? So by increasing the temperature, more particles would have enough kinetic energy to react. So you have a higher percentage of effective collisions, and that translates to a faster rate of reaction. So do we have any questions on this graph? All right, cool. All right, so let's move on to the chemical nature of reactants. We mentioned yesterday that some substances simply react easier than others, right? And this is because those substances that readily react, they have a low activation energy. So this is called the threshold energy. That is the minimum amount of kinetic energy needed to reach the activation energy. So basically, it is the activation energy, okay? Sodium has low activation energy. You don't need a lot of energy to rip away that electron, all right? Whereas gold has high activation energy. It's really hard to rip away an electron from gold. So, if you look at this picture here, you have a curve, all right, that represents the distribution of particles with various kinetic energies. If you have a high activation energy, then your activation energy will be the dash on the right. If you're the dash on the right, only few particles have enough energy to react. The darker green will be the amount of particles that can have effective collisions, which is quite low. All right. If you have a lower threshold activation energy, you have the dash on the left, that means more particles will have sufficient energy So hence a higher percentage of effective collisions there, therefore faster reaction. Okay, is that clear, everyone? The chemical nature changes the activation energy, and the activation energy of a compound is an inherent property of that compound. It is unique to specific compounds. Does that make sense? So that explains why certain things react easily, whereas other things, they don't react so much. All right, so here's another one. Why does catalyst increase the rate of reaction? So a catalyst will reduce the activation energy required for a reaction to happen by providing an alternative pathway. All right, you understand what that means? In order for a reaction to happen, you must have sufficient kinetic energy to collide them together with enough force. If that is the activation energy, it has to be greater or equal to the activation energy. Then you can have a reaction. But what if the activation energy is really high? I don't have enough energy. What do? Well, you can use a catalyst. If you add a catalyst, the activation energy will be reduced to a smaller value, and then more molecules will be able to react. All right, so think of it this way. You want to buy a car. You go to the dealership, and you check out some cars, and you inquire, so how much does this car cost? The person tells you $50,000. You'll be like, oh crap, I don't have $50,000. Then you can't get the car. It's that simple, right? If you want the car, raise $50,000 and come back, which is very hard. You're not going to get $50,000 anytime soon. So is there any alternative? Well, yeah, you don't have to pay the full amount. You can lease the vehicle, or you can finance the vehicle, pay a few $100s every month for a couple of years until you pay the full price. That's very doable. Many people choose that option. You're not going to just whip out $50,000 in cash, so you might as well just pay like a few hundred every month. Okay, that's what most people do. That's how most people get a car. You see, but you still pay the full amount of the car. It's just like over a longer period of time. It's easy to pay a few hundred each month than just straight up 50,000. So basically, that's what a catalyst does. You need to get to the final product. Cool. You need to give me this amount of energy, but I don't have that much energy. Well, no problem. I'm going to break it into several smaller steps. So you just have to satisfy fewer amounts of energy, but you have to do it with many steps. That's easily doable. So you have alternative pathways. You don't have to do it all in one step. You can go in another route that uses less energy. So that's a catalyst. Does that make sense? If you look at the diagram, without a catalyst, the activation energy is quite high. It's to the right. So more particles a very few particles have enough energy. But if you add a catalyst, you reduce the activation energy. So now you shift the activation energy to the left. And once you shift it to the left, you have a higher percentage of particles with enough energy now. Please don't get this confused with temperature. All right, increasing the temperature and adding a catalyst are very different things. They both affect somehow the activation energy. They both do something with the activation energy, but they do different things. A very easy way to distinguish between them is, again, use an analogy with students and marks. You want to get into Waterloo Engineering, let's assume. All right, so you look on the website, so what average do I need? Holy moly, I need 95 average for Waterloo Engineering. Uh-oh. So what average do I have right now? You look on your report card, oh crap, 55. Yeah, I don't think Waterloo will accept a 55. So what do? Let me just go and cry to my teachers and beg them for marks, right? So you come to me, like, please, I'll clean your board, I'll sweep your lab, please help me out here. Like, I'll do extra work. Can you please give me more marks? I'm like, you know what? I like this kid. I'll cut you some slack. You know what? I'm gonna raise your mark from 55 to 95. Here you go. Have a great day. All right, and then your mark is now 95. You apply to Waterloo. They're like, oh yeah, this kid has 95 average. Come on in. So you get into Waterloo because I gave you more marks. You see what I mean? I provided you with what you need to get into university. So that is like raising the temperature. I provide you with the activation energy in order for your reaction to occur. So the activation energy has a really high bar. I'll just give you enough so that you can reach it. What about a catalyst? Well, same thing. You want to get into Waterloo. You look at, I need 95 average. I got 55. What do I do? Let me just talk to Mr. Joe and see whether he can do something. And you come to me crying, so, I really need to get into Waterloo. Please help me out. I'm like, okay, say no more. Let me just phone up my buddies at Waterloo. We go way back. So, hey, man, how you doing? Yeah, I have this kid, really, really nice kid. I like this person a lot. So could you just do me a favor? Yeah, could you just, lower your requirement for this year? Just let this kid in. Like, yeah, no problem. Anything for you, man. So Waterloo lowers their requirement this year from 95 to 55 so that they can accept you. So you get into Waterloo with a 55 because Waterloo lowered their standards. That would be a catalyst. You see, I still helped you. I didn't give you what you need. Waterloo decided to drop the bar. You see what I mean? So you lowered the activation energy so that you will be able to get in. So that's the difference between temperature and catalyst. Please don't get confused. They all have to do with activation energy, but they're not the same. Okay, so do we have any questions? All right, cool. If you want to represent a catalyst using a potential energy diagram, well, this is something that you have to draw. You have, reaction progress on the x-axis, energy on the y-axis, okay? And this is potential energy, to be more specific. So you draw your reactant, you draw your activation energy, you have to go up, okay, to the transition state or the activated complex, and then you have to fall all the way back down into products. The difference between the reactant and the highest point, that would be your activation energy, right? In green, you will have an uncatalyzed reaction. No catalyst, you just have to provide that high of an activation energy. But if you have a catalyst, that's the graph in purple. So you can see that the activation energy is a lot lower, but now you have two humps. Does that make sense? You got to get over two humps, but both of those humps have low energies, and that's very doable. So instead, you will find an alternative. Instead of doing it in all one big step, you take two little steps. Okay, if you have take two little steps, you need less energy, and more molecules are able to achieve this. You will draw the curve that way. Notice that delta H never changes. Delta H for both catalyzed and uncatalyzed remain the same. You don't change the enthalpy. Remember, enthalpy doesn't care how you got there. Okay, that's Hess's law. You just add up all your individual steps. You should get the same number regardless. So please make sure you don't change your enthalpy. All right, so do we have any questions about this? No, so we're good with catalyst. All right then. So let's just finish up with concentration and surface area. Concentration is very easy to understand. If you have fewer molecules, chances are they're not going to collide very often, right? Because there are less things to collide with. Whereas if you have more particles, you have more probability of collision. If you just go walk into traffic blindfolded, if you do that right now on a small road, it's probably fine. There are very few vehicles out there. If you do that during rush hour on Highway 401, that is suicide because you're probably going to get hit. There are more cars on the 401. So more vehicles, higher risk of collision, more molecules, higher probability of collision. So increasing the concentration will increase the frequency of effective collisions, therefore faster reaction rate. Okay, that makes sense, right? All right, so the last one is surface area. I kind of mentioned this yesterday. If you have, let's say a cube, you have 6 sides and you have low surface area. But if you chop up that cube, you now have many sides. You drastically increase your surface area. In order for reaction to happen, they must collide, and you need surface for that. The more surface area you have, the more potential sites for effective collision can occur. So if you have more area to collide, of course you're going to get more effective collisions. So that increases the rate of reaction. So we have basically investigated why the 5 different factors affect the rate of reaction using either a diagram or just common sense. So here is an example. Okay, I'm asking you to explain certain phenomenon using collision theory. So for this example, I have 2. Trees do not spontaneously burst into flames. Okay, you have to explain why using collision theory. Okay, trees don't just catch fire. Well, sometimes they do, like Australia last year, but no, rarely does that happen. Why not? Can somebody go ahead and try to explain using collision theory? Anyone? It's the same reason as the gas station. What's it lacking?
It needs activation energy.
Exactly. You need activation energy. Wood burns with oxygen. No problem. Wood is made of carbon. Right? And oxygen is everywhere. But trees don't catch fire all the time because you don't have enough activation energy. They're colliding, but it's not effective. Okay? So they don't burst into flames because there's no activation energy. Right. So B, a candle burns continuously. Right? A candle burning is just the reaction of oxygen with wax. And you do need to light up the candle, though. You can't just have a candle and it would just burst into flames. So you have to light up the candle. You have to ignite it. But once you do, you don't have to do anything anymore. You can just watch the candle burn until you run out of wax or you run out of oxygen. Okay? It will just continue to keep burning. So why does the candle burn continuously? Okay, that's a tricky question. Do you understand what I'm trying to ask? All you have to do is provide the activation energy once, and then you're done. It's hands-free candle burns. This is not true for, let's say, an endothermic reaction like photosynthesis. You have to constantly bombard the leaf with light in order for the light reaction to happen, right? The moment you turn off the light reaction stops. This is different from a candle. You just have to give it once. You don't need to continually lighting the candle. It will just naturally burn. But why? Don't you need activation energy for every single wax molecule? No? You need activation energy between wax and oxygen, right? And there are many wax molecules in a candle. And you do need activation energy for all of them. But you only lit it once. The reason is, as you burn, it is an exothermic reaction. You release heat as the reaction progresses. And that heat is not wasted. That heat is then being used as the activation energy for another wax molecule. So this generates its own activation energy as it burns because it is releasing heat. You see what I mean? So exothermic reactions are spontaneous. It means they happen by themselves because they release heat to fuel further reaction. This is not true for endothermic reactions. Like boiling water, for example, is endothermic. You need heat for this to happen. The moment you take the kettle off of the stove, the water starts cooling. It does not heat up anymore because you need a continued supply of heat because it doesn't generate its own heat. You see what I mean? So you need to be able to explain certain natural phenomenon using collision theory. You have to use the fact that things need activation energy, and you need to provide the activation energy one way or another. Somehow give me the energy. In this case, the candle releases heat, which generates the activation energy. Okay? All right, so here's example 2. In example 2, it says to draw a potential energy diagram. And on the test, you're probably not going to be able to draw a diagram, but you still need to understand how to do this, okay, because I'll be asking you questions about the potential energy diagram. So magnesium reacts with hydrochloric acid, producing hydrogen gas, magnesium chloride, and 460 kilojoules per mole of energy. Draw a potential energy diagram, label the activation energy, the activated complex, and delta H. On the same diagram, draw another curve to represent the addition of a catalyst. Okay, I'm going to go ahead and give you around like a few minutes, 3 minutes or so, to try to draw this on your own before I show you how to do this properly. I suggest you use pencil. I'll come back in like 3 minutes. All right, so to draw this, first, you have to draw your axes. So on the x-axis, it's reaction progress, or you can just write time. On the y-axis, you have to say potential energy. So please make sure you actually label the axes, because you got to tell me what that means. Sometimes, I remember a couple of times on the test, I made somebody draw this, and I said specifically, label the axis. So cool, the student put X and Y as their labels. I'm like, this is not math class, like what does X and Y stand for? So you have to, in words, say what it is. And also you need to draw a curve. The reactant should have more energy than the product because this is exothermic, as evident from the question. It says it produced 460 kilojoules per mole. If you produce energy, you are exothermic. And also you need the hump for the activation energy. Right, so, and you have to label the activated complex at the top. The difference between the reactant and the activated complex, you have to label as EA. And then, of course, the difference between reactant and product, that's delta H. Actually, that's actually specifically 460 kilojoules per mole. This is with no catalyst. If you draw something with the catalyst, you have to lower the peak of your activated complex. I'm aware you're supposed to have like 2 hills or more. It's just that for this one, I just got lazy. It's really hard for me to animate 2 different hills. So I just drew 1. But if you want to draw 2 or 1 hill, I'll be okay with that. Just make sure it's lower. You have to lower the activation energy. And also, delta H should not change. You can't change delta H because the catalyst will not change your enthalpy. So that would be the new activation energy from the lower activated complex, the reactant. That's EA with the enzyme this time. So that's it. Do we have any questions about this graph right there? You need all of this. You need to label your reactant and products. You need to label your activated complex. You need to draw the curve properly, label the EA, label delta H. And you gotta have everything. Now, you can't draw one on the test, but I will give you a graph and ask you, well, what is this thing in the graph? What does that stand for? So you have to be able to explain the graph. Okay, so we good? All right, so this concludes the lesson on collision theory. So we learned what collision theory is. In order for effective collision to occur, you must have sufficient kinetic energy as well as a proper orientation. And also, in order for a reaction to occur, you need to overcome the activation energy, which is the minimum energy you need for effective collision. You could either have equal or greater than the activation energy for the kinetic energy. And also, we talked about the potential energy diagram, the kinetic energy diagram, and how we can use that to explain why certain factors have an effect on the rate of reaction. So do we have any questions regarding this lesson? All right, that's good.